Hello students, welcome to the class. So today we'll start the new chapter, Equilibrium. So this is chapter number 6 of NCERT. In today's class, we will be dealing with the section 6.1 of the NCERT, which is theory part 1 of our session. This is the disclaimer. Now in this class, our objective would be to look upon the dynamic nature of equilibrium involved in the physical process. So basically, you will notice that equilibrium is broadly divided into two types, and our focus would be on the dynamic part. So there is one more type which is static part. We will not discuss that. Next thing, we'll see the law of equilibrium, and lastly we'll look upon the characteristics of the physical process equilibria. Right, so three things are there. One is what is physical process. We will first see that. We know it already, but we'll just see a glimpse of it. Then we will try to understand the dynamic nature of equilibrium that we observe in physical process. After that, we will state the law of equilibrium, and lastly we will give some common characteristics which is for the physical process equilibria. If I just look on the specific topic according to the NCERT, which is managing this objective, then it is section 6.1, of course, in which we will see equilibrium in physical process. And that one part will be solid liquid equilibrium, then the second will be the liquid vapor equilibrium, and the third will be solid vapor equilibrium. So these are the three phase transitions that we will see. After that, we will look upon the equilibrium that exists in the solution phase. Okay, so during the dissolution of solid or liquid, we also observe a new type of equilibrium. So we will notice that, and at last, of course, we will look at the general characteristics that we will deduce from all these four conditions. So let's begin our discussion. So what is equilibrium? First, we should understand that, and to understand this thing, we have to know three things for sure. The one is equilibrium state. So what is equilibrium state? So this is defined as a state of the system where the physical properties like the pressure, concentration and temperature do not change with time. And the reason behind this is that the opposing forces occurs at the same rate. Next, it is only attainable in the closed system. So this is very important. Although in some cases you will see that the rate of backward and forward reaction is same, but still the reaction is not attaining the equilibrium, and the reason would be that your system is not a closed one but a open one. Okay, so this is very important criteria. Now, the mixture in which the equilibrium is being attained is called as the equilibrium mixture containing the reactants and products. And lastly, we have the dynamic equilibrium. So this is one of a type. I will not go into the second type, static equilibrium. It is not observed popularly, but most of the cases you will see the dynamic equilibrium. Now, what is dynamic equilibrium? So in this part, what happens is that both the forward and backward reaction occurs at the same rate. They don't stop. The forward and backward reaction don't stop. They occur. But due to this equal, I would say, rates, there is no net change that is seen. You can just think of an example. Suppose there is a tank, right, and it is filled half. Now what is happening? Two things are going on. First is you are taking out the water from that tank which is half filled by one bucket, right? And your friend in the next step, so that you are doing alternately, you and your friend. So in the first step, you are taking out the water, and in the second step, your friend is putting the water with the same bucket of the same amount. Since both of these steps are adding and removing the same amount, therefore the net change in the level of water will be nothing. It will be zero. So what you will say, that you are taking water and you are giving water, means the process is going on, but the net change that is observed is zero. So similar to that, we will see the case of dynamic equilibrium. Okay, so we'll try to understand the same with the help of some physical processes. Now, physical processes are much more easier to understand and not that much complex as compared to your chemical process, in which you have to look upon various things like concentration, pressure and all. The physical process are judgeable with your naked eyes. So that's simple to judge, right? So first we will see what is physical process and what types of physical process we are going to look upon for understanding the equilibrium. So the first three major physical changes that we will see are the phase transformations. I've already told you. What are those? First is solid to liquid, second is liquid to gas, and third is gas to solid or solid to gas. So these three kinds will be studied under the physical process. Let us move on to the first one, which is ice-water equilibrium. So we are taking example to understand the solid-liquid equilibrium. To understand this thing, first you have to know that what is melting point or freezing point. So this is very, very important to understand. You must be knowing a primitive definition before I introduce this new definition. So that primitive definition would be the point or the temperature at which the water starts to freeze or a liquid starts to freeze is called as the freezing point, right? So this is the most primitive definition that we have studied till date. But since you are now moving to class 11th and 12th, you must have a standard definition. So that standard definition says that if you are defining the freezing or melting point, first thing you should do is putting a bar on the atmospheric pressure. So the atmospheric pressure is being maintained, 1 atm is taken, and after putting the bar on this pressure, we will define the freezing point or the melting point as the temperature at which the solid and the liquid both have the same vapor pressure. Okay, so this is the basic criteria for the attainment of this freezing point or melting point. So both of them I am saying at the temperature where the vapor pressure or the pressure of the solid and liquid phase becomes equal, given that your atmospheric pressure is maintained, 1 atm is taken. Now what is the meaning of this? What we are trying to say here? To understand this, we will take an example of ice-water equilibrium. We look upon a diagram and then we will try to understand the same. Okay, so we can represent the ice-water equilibrium with a simple equation. I would say this is much general for any other freezing or melting. So you can write melting and then a double-headed arrow, two double-headed arrow with a freezing on the right hand side. So this double-headed arrow that you are seeing here, so it is not that general. So there are two arrows which are oriented in opposite sides. So you can say them as two hooked arrows, right? Now these two hooked arrows represent the case of equilibrium. Now take an example of equilibrium. Suppose we are taking ice and water. I have said that for equilibrium to be attendant in the case of physical process, you must take a closed system. So here is that closed system, a perfectly insulated thermos flask. Now this is not only closed, it is isolated. Here the energy and matter both cannot be exchanged. Now why we are taking so? Because equilibrium is only defined. Listen to it very carefully. Equilibrium for a physical process is only defined at its freezing point or melting point. So this is very important to remember. Not only the pressure is kept constant, but the temperature is also kept constant for the attainment of the equilibrium in ice, water or any physical process. So here we are already known about the thought that the freezing point or the melting point of your water or your ice is 273 Kelvin or 0 degrees Celsius. And the pressure is already defined, which is 1 atm. Okay. Now at this pressure and temperature, we will observe the equilibrium which is existing between the solid state of water and the liquid state of water. So the same thing can be said for this given diagram. Okay, so we have taken a perfectly insulated beaker with a closed lid that is again insulated with the surroundings, and the whole thing is kept at a temperature of 273 Kelvin and 1 atmospheric pressure. Now the question arises, how the vapor pressure is defined for the solid and liquid phase? How do we know that what is vapor pressure? See students, whenever you consider a solid or a liquid phase, your molecules are always moving, or you would say the molecules are in a constant state of motion, both for solid and liquid. Now the difference is only that in case of solid, this constant state of motion is the vibration part. it is remaining at its point. It is not going away from its point. It is just vibrating at that point. But in case of liquid, since the movement is allowed, it can freely float, or you can say it can freely flow. So this is the difference between the molecules motion, but they are in the constant state of motion, that is for sure. Now during this motion, whenever it hits the container, okay, it applies pressure. Got it? And this is the reason we say that, okay, gases apply pressure, liquid do not apply pressure, and same is the case for solid. Of course, some pressure is there, but that is not that much prominent. Now, whenever you want to change the state of a given system, you have to increase its vapor pressure for moving from liquid to gas, and in moving from liquid to solid, you have to decrease its vapor pressure. So here the vapor pressure is that pressure which your molecule is applying on the atmosphere during that movement. Okay. So if the movement is suppose faster, then it is in the liquid phase. If it is comparatively slower, then it is in the solid phase. Now the degree of movement should be according to the solid. Then and then only your liquid will change into solid. You got my point? So something is moving very fast, and that is the required movement for liquid. So the system is in liquid. If its movement is slowed down by decreasing the temperature, by providing less energy to such an extent that its movement is now as per the solid, then in that case your system will become solid. So that is a very simple way to understand the change of phase in terms of molecular motion. Okay, so it is basically the movement thing. If it is slower, it is in solid. If its movement is fast enough to break it in liquid, it becomes liquid, and even at a higher movement, it goes to the gas phase. Got it? And this whole movement thing is changed and controlled by the temperature and the pressure. Got it? Clear? Okay. Now, we will look at the equilibrium again and try to give some final observations on the system. What are those observations? The first is, if this is an equilibrium state, then the mass of ice and water will remain constant. Now, this point is very, very important because this is the basic criteria of equilibrium, that physical quantities will not change, and mass is a physical quantity, so it should remain same. So, mass of ice should also not change at equilibrium, nor should the mass of water. Then, next thing, I've already told you about this part, that whenever you are judging the molecule on the molecular level, judging a state on the molecular level, then the liquid is moving at a faster rate, the liquid molecules are moving at a faster rate, and the solid molecule are moving at a comparatively slower rate. Now, what is the reason for their movement? What is putting a constant? Why do I have to supply energy to increase its movement? What is preventing them from moving fastly? So the reason is very obvious. It is your intermolecular force. Got it? So your intermolecular force is the one which is holding back your molecule from flowing away in the solid form. So when your applied energy is not enough to overcome this intermolecular force, then your liquid molecule, the solid molecule, goes into the liquid phase. Right? Okay? And if your given temperature is harsh enough to change the state of the system, then it will go to the next higher state. So what you can say for this given system, that the rate of melting will be equal to the rate of freezing. Now moving on to the next kind of equilibrium, which is liquid vapor equilibrium. What is this? To understand this, again we have to look at the vapor pressure. We have already dealt a lot about it. So it is the pressure which is exerted by the vapor in the equilibrium with the liquid at a particular temperature. So that is the thing. And where is this pressure coming from? It is coming from the movement of the molecule. Now let us define the boiling point. If you know this vapor pressure, let us define the boiling point. So you can think of boiling as a very simple and a normal process. How? So suppose your molecule which is present in liquid phase wants to go in the gaseous phase. So what is preventing that liquid molecule? Two factors are there which is preventing its escape. What are those? First is the intermolecular attraction, the first thing. Second thing is the atmospheric pressure. Got it? So you can say it in a way that whenever your atmospheric pressure and the vapor pressure of your liquid molecule becomes equal, then your liquid particle goes into the gaseous phase. So this is the part. And what is that pressure it is being experiencing? It is your atmospheric pressure. So you can just define the boiling point as the temperature at which your vapor pressure of the liquid is equals to the external pressure or the atmospheric pressure. Now, it will depend upon, you can say it very well, that boiling point will depend upon the atmospheric pressure. If you suppose you are taking 2 atm atmospheric pressure, then you have to supply more energy to the system for your liquid particle to go into the gaseous phase. Now you can represent this equilibrium again in the form of the double hooked arrow, two double hooked arrow, where your evaporation is in equilibrium with the condensation. Can we take a specific example? Yes, we can take that. We can take again the example of water, where your liquid phase of water and the vapor phase of water are in equilibrium state, and this can be represented with the help of the diagram. If you look in this diagram, then some of the molecules of water are present in the gas phase, which are above the half part. So the upper half part is containing the gas phase and the lower half part is containing the liquid phase. If I ask you, why is it so? So there is a very simple question which we encounter daily. So if you keep liquid and gas in the same bottle, then the liquid will be in the down phase and the gas will be in the up phase. So this is a very normal phenomena. Can you explain this part? Is there any reason behind it? Yes, it's a very simple reason. The whole thing is about density. We know it very well that the density of air is less as compared to the water, so it is on the upper part. As simple as that, and that is also applied to the liquid and liquid case. Now, what are the observations from this beaker? What we can see? We can see that initially the rate of evaporation is more as compared to the rate of condensation. So what will happen initially? The pressure will increase when there is the start of evaporation. It will start to evaporate, and at a point you will see that it is stopped, means the pressure has become constant. At what point? When the evaporation and condensation occurs at the same rate. So initially there is only evaporation, there is some sort of condensation, but it is not enough to keep the pressure constant. But after some time, when the amount of liquid is enough, I would say the amount of vapor is enough in the open area, in the closed system, then at that point your rate of evaporation becomes equals to rate of condensation and the pressure becomes constant. Now, next part is evaporation. So this thing that we have seen just now is the case of evaporation and not boiling. Now what is evaporation? Evaporation is simply the conversion of liquid into gas without reaching its boiling point. And what are the things which affects the time taken for the complete evaporation? So three things are there. First is nature of liquid. If your liquid is much more volatile, it will take less time to be converted into the gas phase. Second thing is surface area. So greater is the surface area, smaller is the time taken by the liquid to evaporate. And the third thing is temperature. More temperature you give, more kinetic energy the liquid gets, and easily it evaporates. Now if I ask you, why is the surface area playing a major role here? What can be the reason for this? So it's very simple. When you are increasing the surface area, in a way you are increasing the exposure of the liquid to the atmosphere. Means more and more water molecules are probable to go into the gaseous phase. Okay. See, you can think of it in a simple way. Suppose there is a red ball, right? And it is inside the heap of a blue ball. So you're taking a cluster of blue balls and you're placing a red ball in between them, in middle part of it. This is the first situation. In the second situation, you are adding more blue balls upon this layer, then what will happen? Red ball will go downer and down. It will be now difficult for you to take out that red ball out of the blue ball, because now it is in a deeper situation as compared to the previous one. Or you can say that it is inside the bulk. Similar to that, if your liquid is much more exposed to the environment, it is much more I would say prolonged for the exposure or conversion to the gas phase. Got it? Now, can we understand this with the help of an experiment? So there is an experiment. There are several parts of it. First, what we will do, we will take anhydrous calcium chloride, which is there in a transparent box, and this transparent box is being fitted with a U2 manometer. Here is your U2 manometer. What it does, it helps us to see the pressure changes. You can see that initially the meniscus of the mercury, so there is liquid filled inside it, so the meniscus of the mercury is equal on both sides. And what we do, we initially put anhydrous calcium chloride in it. What it does, the anhydrous calcium chloride, it acts as a drying agent, means it removes water from the transparent glass. So this is the first part that we have done. Now, next is what? Next is introducing the water bucket into the transparent box. Okay, so this is the second part. What we have done, we have introduced a water filled vessel in this transparent box after removing all the moisture from it. Why we are doing it? So that we can only study the changes that is occurring due to this vessel of water and not due to the water vapor that are already present. So we are removing the previous part to study it more efficiently. Now, if this is done, then what is seen? If you look at the diagram here, you can clearly observe what? That the water begins to evaporate. And what is the sign of it? The sign of it is increasing vapor pressure. See, if you look at the meniscus now, the meniscus is now moved on to the right side. Now something is pushing this meniscus from the left hand side so that it is moving on to the right hand side, and that is nothing but your vapor pressure due to the liquid's evaporation. Okay, clear? Now, this increasing pressure will push this meniscus further and further, and the mercury level will rise on the right hand limb. Okay, you can see it very clearly on the right limb. It is rising, and this will rise until and unless there is a stop. We will observe this whole process. Now, gradually, at last, you will see that the meniscus rise on the right hand limb is stopped after some time, and this indicates that your pressure is now constant, means there is no net change of vapor pressure due to the liquid, and this indicates that your dynamic equilibrium is attained. So what you can say at the point when the mercury stops rising, you can say that now there is no net change in the concentration of water vapor inside the transparent box, due to which the pressure is now constant and the system has attained the dynamic equilibrium. At this point, the rate of evaporation is equal to the rate of condensation. So two parts are already discussed, which is liquid and vapor, okay, and solid and liquid. Now we will move on to the third phase transformation, which is solid and vapor equilibrium. What is this kind of equilibrium? To understand this, first you should know sublimation. For those who don't know, let me tell it in your simple words. So it is simply the conversion of solid directly into the gaseous state. You must have observed some substances like camphor, naphthalene balls, which I would say decay with time, whose solid particles decay with time, so they gets converted into the gaseous phase without getting converted into the intermediate liquid state. So this process is called sublimation, and the opposite of this, which is conversion of the gaseous vapor back into the solid state, is called as deposition. You can represent its equilibrium with the help of, again, the normal equation, sublimation, double hooked arrow, then we have the deposition. Can we take an example of the same? So here we have taken the sublimation of iodine. Suppose we are taking solid iodine in a closed vessel. Now what will happen? As you take it, you will see a equilibrium that is existing, and that equilibrium is existing between the solid phase of the iodine and the vapor phase of the iodine. Now, how can we observe it? we can observe this thing with the help of intensity of the violet color. So you will notice that initially when you introduce this iodine crystals inside the container, then the air inside it is completely transparent. So that is very normal. But as soon as this iodine starts to evaporate, you will observe that the color of the air around the crystal is changing and it is becoming violet and violet. So it is intensifying in the violet color. Now at equilibrium, the intensity of this violet iodine vapor becomes constant. Okay, so this is the second part. Initially, you will see that the air is transparent inside the container. After some time, the intensity starts to rise and it changes. And after some time, when the equilibrium is attained, means the sublimation and the deposition process occurs at the same rate. Then in that condition, we say that the intensity of violet color is not changing, so the equilibrium is attained. So what we can say at this point, that sublimation is equals to the deposition. So three phase transformations are being now discussed. Now we will move on to the next kind of physical process in which we can observe equilibrium, and that is dissolution of solid in liquid. Means dissolving the solids in liquids. So whenever you are adding a solid solute to a liquid solvent, then the rate of dissolution and crystallization becomes equal at equilibrium, and that results in a saturated solution. So you start adding solid solute to a liquid solvent. After some time, you will observe that no more crystals can be added or dissolved at a given temperature, and at that temperature you say that okay, we have attained the equilibrium and the solution is now saturated. Now what is saturated solution? You already know it. It is the maximum amount of solute that can be held by a solvent at a given temperature and pressure. And you can take a very simple example. Suppose we have a sugar and we have two phases of it, solution phase and solid phase. Then in that case, if you are taking a saturated solution and you are adding more sugar to it, what will happen? You will see that the sugar starts to deposit it in the bottom of the vessel, because now the solution has already the maximum amount of sugar that it can hold. As a result of this, you will not see any further dissolution of sugar particles into the solution. Okay, is it clear? Now if you take this example and try to understand that what is happening at the molecular level. So at equilibrium, what is happening? The rate of dissolution is becoming equal to the rate of crystallization, right? Due to this, you cannot add further crystals of sugar in it, and whatever you add, it will go back into the solid phase. But question is that, is this solid sugar that is deposited in the bottom, is it still, or is there any movement inside this? You got it? So suppose you are putting sugar solution in a saturated solution again and again, although it is saturated. So is the sugar that you have put after the saturation is the only one that is deposited in the bottom? No, it's not the case. Once you start adding the sugar into this saturated solution, the extra sugar that you have added is in a way going into the solution and kicking out the molecules that are already dissolved in the sugar. Right? So you can think it of in a way. Suppose there are 4 balls in a row. Right? You must have seen the Coco game. If you have seen the Coco game, you must have seen there that whenever a person sits, it pushes the other one who was already sitting, and then it sits in the place of that. Right? So take for example, there are 5 cubes. Okay, so suppose there is a box in which 5 cubes can be accommodated. Now you have to put the 6th cube. That one is more important than the previous 5 cube. What you will do? You will take out the 5th cube and put the 6th cube that you have already have. But now the number of cube is already same. It is 5 only. But the identity is changed. Now the 6th cube is placed in place of the 5th cube. Similar to that, when you add solid particles into a saturated solution, that solid particle which you have added, it kicks out the previous dissolved solid particle and goes into the solution. But this process is done in such a way that there is no change in the solubility, or I would say the concentration of the solute in the solvent. Got it? Clear? Okay, moving on to the dissolution of gas in liquid. So if you are taking a gas in liquid, we can take the example of what? We can take the example of the CO2 dissolved in soft drinks. What is the process that is happening in this? Your gas molecules are entering the liquids and your gas molecules are leaving the liquid. So this will happen at equilibrium structure. What example can we take? So you can simply take the example of CO2 gas in soda water in a steel tube. So that is a classic example of gas dissolved in solid. In that case, if you try to add more gas to the solution, then what will happen? It will kick out the existing gas in the liquid and go into the solution. And this process is always going inside a container. Suppose you are seeing a Coke bottle. Now the upper part of the Coke bottle contains the gas. Got it? And the lower part contains the liquid. But is it so that the gas that is present on the top of the liquid is still? No, it is not still. Some molecules of that gas is always going into the solution and some molecules of the gas which is present inside the solution is coming out. So this process is going on continuously. So that bottle is representing a dynamic situation. Got it? Here a very simple thing is applied, which is Henry's law. So I'm just introducing it here to you because questions are asked on the basis of this law. So basically it says that the mass of the gaseous particle that you want to dissolve in a given solvent depends upon the pressure. Greater the pressure you applied, more the gaseous particle goes into the solution. And it is given by the equation mass dissolved in a solution is equals to kHp, where P is the pressure, so it is directly proportional to the pressure and is proportionated by a Henry's constant. So this can be the illustration of the same. See, you can see here the red arrows is depicting that your gaseous particles which are in the solution are coming out, and at the same time your gaseous particles which are out of the solution are going into the solution. So they are moving downwards. So this is shown by the black arrow. Right? So this is going on continuously, and the same thing happens in a Coke bottle as well. Now we can define the characteristics of physical equilibrium. First is equilibrium is always observed in a closed system and at a constant temperature. So two things are important here. Second is it is only seen when the rate of forward and the backward reaction becomes equal, and there is no static equilibrium in case of physical process. There is always a case of dynamic equilibrium. Then at this point where the equilibrium is attained, all the measurable properties like your pressure, your mass, your temperature, they all become constant, or they all remain constant. Then what are these physical processes? So it is written here. So pressure and concentration. Then the magnitude shows the extent to which a physical process has progressed before reaching equilibrium. So we have seen all the part of the physical process. So let us summarize all this. So what is equilibrium? It is a dynamic process in a closed system where the physical properties do not change with time. Now, to understand this physical process, we have dealt with two kind of transformations, phase transformations and the dissolution of various things into the liquid. If I talk about this physical process, the first one is solid liquid, that is related to phase transformation. Then we have the liquid vapor, and lastly we have the solid vapor. In case of the dissolution, we have dissolution of solid into the liquid, then we have the dissolution of gases into the liquid. You can take the example of saturated sugar solution in which the extra sugar is added. Then in that case your beaker is always in the state of dynamic equilibrium. So this was all for today's lecture. Thank you for attending the session. I hope you enjoyed it.